Alright, so we are trying to introduce a three-phase circuit, but to do that you have to understand three-phase, right? Three-phase system. So three-phase AC current, alternating current, right? Okay. So here, because we have to understand the generation, we have to understand, revise something, right? So if you know that if we have a magnet of this sort, right? One thing that we can say is that it has poles, north and south pole, right? And then the magnetic lines or the magnetic flux, the direction from the what do you call it, the north to the south, right? So this way, right? So move from the north to the south. The same here, north to the south. Okay. The same here. So move out of the north pole and enter the south pole, right? Okay. So what happens if we mount this magnet onto a shaft, right? So what we're having here, the green thing I'm having here is sort of a shaft, right? And then if we put that in a system, and then we put some kind of like turbines on it, right? Something like turbines, whether wind or water content. So in the system, for instance, so you see our magnet is here, our shaft is inside this turbine. So as the water moves from what do you call it, up to down, right? So it turns this one this way. So as it turns the shaft as well, right? So this is the basic thing, but we're going to look at the diagrams to understand what's happening. So though we are seeing four diagrams here, we are going to consider just one. So like it's from one we go to two, right, and we go to three, right, and finally move to four. It's steps, right? But we just want to see what's happening. That's why they've been arranged this way, right? But at the moment, let's concentrate on one. So let's look at what's happening. Right. So we have the magnet here, as we said, right? It has been mounted on the shaft. That's why we have some kind of green color there, right? And then we have a coil, right? Not definitely an inductor or something, but let's say coil, wire windings, right? Wire coils, wire windings around it. So when you see, because you have this, there's just one set, you see it as one, so it's just the same thing, right? So that's why we have the same color code there, right? So what's happening is that now that the magnet is the pulse of the magnet is further away from the coils, right? There's basically no what's the name? No current flowing through the coils, right? But we call there's a term for that one. We call it electromagnetic induction. What happens is that the magnetic flux flows through across the coil, right, and induces a current through it. So as it induces a current through it, right, that's what happens to make the bulb to light up. So here's the case that we have the poles of the what do you call it, the magnet furthest away from the coil, right? So it means that there is no induced current within the coil, right? So it turns as it continues to turn, right? And the thing is that as it gets closer to the coil, the what do you call it, the induced current across the coil increases as it gets closer. So it increases as until it gets to this one like this, right? But now let's look at the direction of the current, right? So as we said the current flows, magnetic flux, magnet, right? It flows from the north pole to south pole. We know the red is the north, blue is the south, right? So it moves this way. So something like this. So we have the magnetic flux, right? But the direction is from the north to south, 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 right? So as it goes this way and it passes across the coil, it induces some current, right? So as a result, we have let's see, we have the current induced this way. So the current passes through this coil system here, the circuit here, and of course the current to flow and the bulb lights up here. But you see here, the magnet poles, right, are further away from the coil, so there's no induced current. But here they are closer to the coil, so here basically they are the maximum, right? So that's why the bulb is brightest here, right? So as it moves, going to 10 in 1 year, going to 10 10 10, increase until it gets to its maximum, and the current flows in this direction, right? So there's the current, right? Okay, so then when we look at the way, you see that as it continues to turn, right, the red turns, so we are going in this direction, right? As it turn, because it is brightest here, right, as it continues to turn, the current or the voltage across it decreases, right? So as a result, it dims. So at the moment when it gets to this position here, when the magnet is in this position, the 3 here, the what do you call it, the voltage or current across the coils here are minimum, right? So the bulb turns dark again, right? But as it continues to turn, right, when it continues to turn, you see that it increases again until it gets to this side, right? And the bulb is brighter here again. But let's look at this again. You see that the orientation of the magnet here is different. For in the second one, in 2 here, we have north to be on the right side, south to be on the left side, but here we have south to be on the right side, not on the right side, right? So meaning that there'll be a reverse polarity of the current, right? And we said the magnetic flux move from the north to south, so something like this, right? When you have something like this, something like this, that will mean that the current will flow this way. Sorry, the magnetic flux direction is this way, so as a result, the current this way, right? It uses a current in this way, so the current moves in this direction, opposite direction. As a result, it will move this way, right? So then again, because it's the magnet poles, the poles of the magnet are closer to the coils, the what do you call it, the bulb here is brightest again, right? But then we're going to look at this using the diagram. Here we're thinking about, we're just going to use one of them. We said apply electricity, the basic equation is basically IR, but here's the case we are using R, but you can use voltage as well, because the sinusoidal quantities could either be voltage or current, but here we're using current, right? So let's see. So meaning that at 1, where the magnet is furthest away from the coils, right, the current there is 0. But as it moves. So this is the position 1, position 2, position 3, position 4, right? So as it moves, as the magnet continues to turn, it increases until it increases. Let's clean this up. So as the magnet turns, it increases until it gets to the maximum here, right? So the 2 here, the maximum position, the one in blue, is the position here. So that's where the current is maximum here. But as it continues to turn, right, to the extent that the poles are furthest away from the coils, it decreases, right? So basically this is the current or the sinusoidal quantity generation. So it decreases again, decreases. So at position 3, you see that the current is 0, right? So it decreases at position 3, which we have here. You see, then again the magnetic poles are further away from the coils, so 0 again, because it doesn't induce any current, electric current through the inductor, right, or through the wires, the wire coils, right? So that's what's happening there, right? That's what's happening. So that's what's happening. Okay, so as we continue from 3 to 4, that's what will happen, right? So you see now, as we talked about polarity again, now that it's turning in the opposite direction, meaning that polarity will change, and as a result, the current waveform to change, like to be reversed, something like that, right? So the same procedure, as it moves from 3, it turns from position 3 to position 4, as we see in the diagrams. It moves from 0, right, and it gets to negative. Move from 0 and it gets to negative 0 and gets to negative. So it moves from 0 and then gets to negative, right? And then now that is getting to 4, meaning that it's getting to the point where what's the name? So the moment it gets to 4, as we see here, meaning that the current is maximum again, but what? Negative, not negative in the sense that, that's negative in the sense of direction, right? Because here we choose a particular direction, but then when we get to a particular point, the direction is reversed. So that's why it's negative here. So negative I max, right? And then it moves up, right, until 0. So that's if it continues and then turns to its original position, as we see in 1. So this right here is 1 cycle, right? This one right here is 1 cycle. So 1 cycle, this 1 cycle, right? Yeah. So basically that's what happened. And if you have a setup like this, where you have just 1 coil, and then we are generating the AC, and we have just 1 coil. This is what we call single phase, right? Why? Because the wire winding is just 1 set, right? Just 1 set. That's what we call wire winding. Okay. And for the single circuit, for the single phase, this is what happens. Because we have what's the name? Just 1 phase, meaning that when we plot the current and the voltage, this is how it would be. This yellow and purple line, right? But if you plot, you try to find the waveform for the power, this is how it would be. Let's see, which is the red curve that we are seeing there. We are just going to go very quick. So for that one, it moves from 0. It moves from 0, get to the maximum, and then from the maximum gets to 0, right? This is basically a plot as a result of these 2 voltage and current waveforms here, right? So here we are considering purely resistive. We are just using that as an example, right? and then the power from 0 increases again continuously. That's how it happens. But this is for, what do you call it, single phase. Why? Because we have just one wire winding. Okay. But then if we manage somehow, right, to make sure that the wire windings around the magnet is more than one, right? So let's see, because we have blue here, this one set, red here is one set, this blue is one set, this yellow is another set, right? So it means that as the magnet rotates, there's a less chance that there will be a point where the, what do you call, the bulb is dark. Why? Because at every point in time, even if it's closest to this one, to be the brightest here, right? A minute. Let's clean this up and see so we can. But this is just the understanding, right? If you don't need this, you can skip to the next part. Okay. So then at this moment here, as we can see, is the poles are closest to this one, right? So it induce a current in this one, right? And as a result, the what do you call it? The bulb will be brightest, right? But as it turns, because the turn is in this direction, right? As it turns, to get to a point here, it doesn't go completely dim, right? Why? Because as it gets here, it moves towards the red coils, windings, it gets brightest again. So there's less chance that it goes completely dim, right? So it turns, get to blue, right? So continues, right? So this is what we call a three phase, right? So basically, this is the whole setup. This is the, what do you call it, the general representation, right? Okay, but let's look at this. And because of how this is, that we're having the magnet turning at, and then at every point in time, it's either moving away from one coil and getting to another coil. As we said that the power is almost not zero. There's no point in time that is zero, right? So basically, it's able to give the bulb some brightness at every point in time, right? So as a result, let's see. You see, we have three wire windings. We have yellow, we have blue, and we have what, red, right? So we are going to look at that. Just the understanding part. That's so we did, right? So we have blue, we have yellow, and then we have red, right? So the lines that we are seeing, the ones that go this way. So let's see. These ones are the sinusoidal quantities, whether the voltage or the current, right? We have the yellow as well. And then we have the red as well. Right, the red as well. Okay. But then those are not the ones we are interested in. We're interested in the power, right? So what's happening is that, as we were saying, it turns and it gets to, as it moves away from one coil, it gets into another coil, right? The ends of the poles get to another coil, as we've seen in this diagram here, as it turns, right? Okay. So that's what happened. Unlike the one we have just one coil, this one we have three coils, right? So the power, this is how the power will be, right? So as the power increases from zero, the total power of the system, because it's three phase, as it increases from zero, it moves from zero to maximum peak, and it's about to go down. It doesn't go down completely, right? Because it ends up getting closer to another wire windings again. So then the power increases again to maximum peak in the yellow winding, right? And it starts to decrease again because it's moving away from the yellow windings. So as it's moving, getting close to zero, it gets closer to another winding, the blue wind, the wire winding, right? And it gets to maximum again, right? So that's where we end up getting the power waveform to be like this. There's the green shaded side, because we are doing what, three phase, right? We're doing three phase. So let's look at this. Let's just see. So within one cycle of the three phase, it could behave something like this, unlike the single phase, right? So this is the baseline of the whole graph, right? There's a zero. But you see that the power here moves, it gets here, it doesn't go to zero, and it rises again. It doesn't get to zero, rises again, right? So to continue something like that, right? So it doesn't get to this zero here, but for the single phase, it moves from zero, goes up, go to peak, and then come back to zero, right? But for the three phase, this is how what happens. So this is why we say that for the three phase, what happens is that we get a more efficient system. Why? Because it's able to give you much better power, right? Which doesn't go completely to zero, like moves from zero to peak, and then from peak to zero. No. It moves from zero, goes up and comes down slightly, not completely to zero, right? So always there's some kind of power within the system. It doesn't go completely off. So you can see that this kind of like gives you better power, efficient system, right? But one thing we should notice that is that because three things are coming from the same system, we are doing three phase. We see that we arrange them in such a way that the windings are, what do you call it, are evenly or symmetrically distributed, right? Or what do you call it, evenly apart from each other. So if you have one phase, so let's see now I'm measuring from the yellow to the blue phase, right? So the phase angle between them is 180 degrees, right? So now if you are measuring from the, let's say from the red to yellow, it will still be the same thing where we have 120 degrees, and from this blue to red still be the same. So in a three phase system, they are 120 degrees phase difference degrees apart from each other. So that's the three phase system, right? All right. But then we should take notice that we don't only have the three. We have one phase, two phase, three phase, six, a lot. But the one that they've seen to be efficient in our current system is the three phase, right? This one is commonly used in commercial systems. It's used a lot amongst all the phases that we have, the phase system that we have, right? Okay. So then when it comes to three phase circuits or three phase systems, it's either that you're having a supply system that's three phase, or you have a load system that's three phase, right? So it could be that whatever it is that you're having is a load system, right? Or a generator. Generator means it's supply, right? But whatever it is that happens, it means that it's either a load, it's either a supply system, right? Or a load system, right? And then whatever it is, because there are three phases, there are main ways that we arrange the three phases. Could that be in star arrangement? So let's see if they are loads, right? We have three loads, right? One load here. Oh, okay. One load here. Let's see something else. Okay. One load here, another load here, and another load here, right? And then we see that these are the common ways of arranging the three phase systems. In the sense that, let's go back to this one, right? So this is one wire winding, there's another wire winding, there's one wire, another wire winding, right? But we see that if this is a circuit, if this yellow wire winding is one circuit, right? This is the start, this is the end, right? And this is the start, this is the end, right? And this is the start, this is the end, right? So they are, if we try and then just represent the starting of them, we get to see that they are kind of like, one way to write them, it will be in the star system. So let's see the star arrangement that we are talking about. Let's see if we can do that. Okay, so if we manage to take this off, let's clean them up. So here, let's disconnect from this. Let's take the bulb and the wires out, right? Let's take the magnet out as well. Okay. All right. Oh, there was this one yellow here. So this is the yellow is here. So if we take the endings out, so we've taken the end of the yellow out, you're taking the end of the red out, you're taking the end of the blue. Minutes. We take the end of the yellow out, we take the end of the red out, and we take the end of the blue out. You get something like this. So the first arrangement that we kind of like talk about will be the star, right? And from this we build. So this one way of rearranging the whole complex thing that we're seeing. So we have something like this. We have a neutral point. This is the star. We have a neutral point, right? It's connected here. We have this two connecting here, this two connecting here. We end up getting a star. And then another way to rearrange all this is to rearrange them in this way. So this right here is a star. This right here is a delta. It's delta. This right here is the delta. All right. Yeah. So this is the introduction to three-phase circuit. What do you call it? Three-phase quantities generation, right? And then how we the general ways that represent them, star and delta. Right.